So the second speaker in this morning's session is Nader Engheta. He's professor of electrical engineering at the University of Pennsylvania. Dr. Engheta received his bachelor's degree at the University of Tehran in Iran. He received his master's degree and PhD degree from Caltech. He has a very wide range of interests. Makes it hard to pigeonhole him, but let's say he's made significant contributions to the fields of metamaterials, transformation optics, nanophotonics, and related disciplines. Perhaps he is best known for his invention of the field of optical metatronics. And the idea of this, I hope he will explain it to us. I will do a poor job, I fear, is to develop nanostructures which act as lumped elements, but for an optical circuit. And by putting these components together, for example, on an optical chip, you can synthesize complex optical circuits. So please help me in welcoming Professor Engheta to our symposium.
Thank you very much. Thank you very much, Bob. It's a pleasure and honor for me to be here. I'd like to thank the organizer, Professor Bob Boyd, Professor Paul Kirkham, and Dr. Ben Sussman, and all the members of the organizing committee for bringing all of us here in this wonderful event. And it's really, truly a pleasure and honor for me to be part of this event. Now, it was mentioned by Professor Harosh that this year is a special year for all of us in the field of optics and photonics for a variety of these historical anniversaries that happening going back to 1,000 years ago and to 150 years of Maxwell's equations. A few months ago, in month of July, I was asked by IEEE to give a talk in the occasion of the 150th anniversary of Maxwell's equations, the equations that we love and we use, every day in our work. So in preparing my talk for that historical, perspective of Maxwell's, I said to myself, of course, Maxwell's equations, we use them all the time and wonderful, but just out of curiosity, what are the other equations that, have changed significantly the development of science and technology in human history? So the first thing we did, just Google it to see what we get. And when I Googled that, I came across this book by Professor Ewan Stewart, who's a mathematician and science writer in England. The title of his book is In Pursuit of the Unknown, 17 Equations That Changed the World. So just for fun, let's go over the 17 equations in chronological order. Maxwell's equation would be number 11. It's just a chronological order. So which equation do you think is the earliest one that, according to Professor Stewart, really changed the human history? Goes back to Pythagoras' theorem. A squared plus b squared equal to c squared. Of course, we take it for granted, but indeed, it goes very important, 530 BC. Next one, John Neper, 16-term logarithm. And of course, Isaac Newton, the definition of the derivative. By the way, Newton has 2 of them of this 17, and there's another scientist has 2 of them. We'll get to that. And Newton, of course, for gravitational law of gravity. D'Alembert, 1746, wave equations. Moving along, Euler. Now this one, by the way, was very interesting to me. I squared equal to -1. Of course, we do that all the time, but it's one of the 17 equations according to Stewart. Important. By the way, Euler has 2 of them. He's another scientist that has 2 of them. In the Euler formula for Polyhedra, which was basically the foundation of the field of topology. And the Gauss for normal distributions. Fourier, of course, use them every day. And Navier-Stokes equation actually predates Maxwell's equation. And of course, our beloved Maxwell's equations we have in 1865, Boltzmann's second law of thermodynamics, Einstein, the relativity, Schrödinger equation, 1927, Claude Shannon, information theory, of course. Now, Robert May, 1975, in chaos theory, is coming to the years that some of us have been born. So it's becoming more close. And Black and Scholl equation, 1990s, for financial market and the derivative. By the way, this was the only one I didn't know anything about. So I asked my daughter, who's in the area of finance. She said, yes, actually, this is an important equation. So I trust her judgment. And so also I'd like to share with you some, personal observation of this special year of 150th anniversary of Maxwell's equations. A few months ago in February of this year, I had the privilege to be in a conference in the Royal Society in London called the Faraday Discussions. It's a very interesting conference, by the way. I can tell you offline, interesting format it has. And after the banquet in the Royal Society, we were walking around, and there was these windows around the hall that they have, historical items, in these windows. And one of the students came to me. He says, come here. It's a very interesting item I would like you to see in this window. And when I went there, he showed me the original manuscript by Maxwell, the way he had handwritten it. So I took my iPhone and took a picture. This is it. This is the original paper by Maxwell. And you notice the speed of light, showing up right over here. And right next to it, there was an interesting historical description of this manuscript that he had submitted that. And guess who was the editor of the Philosophical Transaction of the Royal Society who received this manuscript? George Stokes. Stokes' parameter. He was the secretary of the transaction. Maxwell submitted it in October 27, 1864. It was read in December 8, 1864. And it went to the printer June 16, 1865. And particularly, I love this sentence that they highlighted over here. It says, the agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. And arguably, with that sentence, he changed the world. And that's why we are here after 150 years of a lot of development that originated from Maxwell, and we get over here. But just before I leave it, one other piece of interesting history. Right next to it, it shows actually who reviewed this paper, by the way. It's interesting. Actually, Stokes reviewed it, but he sent it also to Lord Kelvin. And this is a note that Lord Kelvin has written on March 15, 1865. My dear Stokes, I'm sorry to have kept Maxwell's paper so long. I read it nearly through with great interest almost immediately after it came to me, and I think it most decidedly suitable for publication in the Transactions. If you can allow me to keep it a few days longer, I would be glad to have it till Monday, and unless I hear from you, I shall pass it on Monday. I guess something never changed. Reviewers are always late. They need more time. So anyway, there is this past 150 years, you heard from beautiful talk by Professor Harosh that there's a lot of scientific and technological development has happened. And in fact, you can view that as coming from the two processes. One is how we can actually control the path of charge carriers, and that would be for fermions. And another one is how to manipulate and tailor electromagnetic waves, how to manipulate photons. And indeed, if you look at all the technological development, you can distribute it into these two categories. In fact, if you look at this, nightmare circuit diagram that the people in electrical engineering like to forget, essentially what we have over here is manipulating where the charges go. And that's what it leads to interesting, functionality. Now, in the case of photons, we need to have materials in order to interact and to manipulate photons. And in the past several years, the field of metamaterial, or the artificially engineering material such that it will have the parameters you like to have, not what nature has given us, have evolved quite significantly because of the process of nanoscience and nanofabrications. And indeed, in the concept of metamaterial is that you try to embed a material with other type of inclusions in order to have a bulk property, to have different collective effect rather than the local individual effect. And this will show up, of course, in parametrization of the material, namely the parameters we love to use, interaction of light with the macroscopic structures like permittivity, permeability, nonlinear susceptibility, and so on and so forth. In my group, we are interested to look at some of the extreme scenarios of this ability to control light-matter interaction. And one of the extreme platforms that we are studying is, of course, combining the concept of metamaterial, light-matter interaction with the one-atom thick structures, and that's, of course, graphene. And that, indeed, will give us the possibility of having optical devices that would be one atom thick. So that would be extreme in dimensionality. And one of the things we are working in it right now is how to actually have a hybrid system of these one-atom thick structures with the dielectric structure in order to have man-made type of like carbon nanotube, but not what nature has given us. Carbon nanotube that you would like to have with the dimensionality you like to have. Another extreme scenario we're considering is time reversal symmetry breaking in the extreme near field of some of these, structure like plasmonic structures. And what you see over here is a very interesting optical vortex result of our simulation that will show that in the very extreme near field, very, very small compared to the wavelength, you can have actually very interesting optical vortices. And that allowed us to actually suggest a very interesting device that would be an optical circulator, but at the nanoscale. Circulator that when the photons come over here will go in this direction, but when the photon coming back reflected, it doesn't go there, it will go over here. So the time reversal symmetry is broken, but it's broken in the nanoscale. Another extreme scenario we are studying right now is what my good friend Bob referred to, and that is the area of optical metatronics that we introduced in my group. And what it is to actually get inspiration from electronics, that we have lumped circuit element in electronics, like resistor, capacitor, inductor, and how to have those lumped circuitry in the photonics, to have nanoparticles that behave as lumped circuit element. And that will give you an interesting toolbox to actually look at the design from electronics, nanoelectronics, and bring it directly one-to-one correspondence into photonics. And one of the things we're working on these aspects right now is to actually look at the possibility of putting this nanostructure next to each other in order to allow the light to do mathematical operations. In other words, let the wave do the math, as I like to call it, or to call it photonic calculus. So this is what I call it the informatic metastructures, that by having a layered structure, or it could be nanoparticles, you actually design a system that as the light goes through this, the output becomes the result of a mathematical operation of your choice on the arbitrary input. So essentially, you have kind of like an analog computer, but in the nanoscale and using light. And another extreme scenarios we are studying is how to actually design structure that would have light parameters would be near zero, like permittivity being near zero, permeability being near zero, index of refraction being near zero, and what other implication, both from wave physics and from quantum optics, we can actually get out of this. For example, one of the aspects of this structure is that you can have a very strange, I call it strange or extreme cavities that would actually deals with light and wave propagation in a very unusual way. So in my talk today, I'm going to concentrate on this last part to see how the extreme scenario in the material parameters can actually help us to look at some of the unusual light-matter interaction. So let's go towards that direction. So let's start again from our Maxwell's equation that we love very much. So if you look at the source-free, time harmonic, macroscopic Maxwell's equation in the classical electrodynamics, obviously we're all familiar with that and we love to use them. Now we all know, by the way, if the frequency of operation is zero, in other words, if you have a DC signal, electricity and magnetism would be decoupled. In fact, that's how Maxwell and Faraday in the 19th century tried to show that if you have a dynamic field, then electricity and magnetism would be coupled. And that's what we have, Maxwell's equation. So we ask ourselves this strange question. Is it possible to design structures such that at the given frequency of interest, the effective permittivity and effective permeability will be zero? And if such a structure is possible, then Maxwell's equation will be decoupled. But this is not a regular decoupling that we see in the DC scenario, because we have the field that's actually oscillating with the frequency omega that you like to have. But if you design the material that at the frequency of operation, you have effective permittivity and permeability near zero, then macroscopically, and I emphasize macroscopically and effectively, electricity and magnetism will be decoupled. Now, what's the implication of that? Well, one thing is that from the distribution point of view, it's actually quite oxymoron structure. In other words, from temporal point of view, they're dynamics, because they're varying with time. But from spatial distribution point of view, would be just like a static distribution. Now, why is that? Because the index of refraction is near zero. It means at the frequency of operation, your effective wavelength is very long. So every structure looks small. Now, one thing I'd like to say right from the start, sometime when I give a talk, people ask me this question, wait a second, if your n is equal to zero, your phase velocity would be greater than velocity of light. Are you violating causality? No. The system is a dispersive system. Group velocity and energy velocity is less than velocity of light. We are all okay. These are all causal. But the phase velocity in the CW system is actually 0, and that's perfectly fine. So that's what I call it. Colloquially, I call it static optics. Although I realize that this is an oxymoron terminology, because how come optics can be static and how come static can be optics? But you're going to see in the result I show that indeed this could be an interesting terminology for them. So in order to get into this, let me take you back in the history about 10 years ago. 10 years ago in my group, we introduced the concept of epsilon near 0 structure. So only one of them equal to 0 first. So back in 2005, we introduced this concept of epsilon near 0 structure, and we discovered an interesting phenomena that will come from this structure. So let me take you back 10 years ago, and I tell you how actually we came up with this question. We started with a very simple question. Imagine that you have a parallel plate waveguides with a metallic wall, impenetrable wall, simplest possible waveguide you consider, and you have a TEM mode, which is the simplest possible mode, coming down this waveguide. Okay? And imagine you have another waveguide very similar to that, not necessarily coplanar. It could be any angle you want over there. And the question we pose is, what would happen if I connect these two waveguides in a very arbitrary way? Completely arbitrary. Now, what would you expect that the mode to see this structure? When the mode comes over here, you see this transition, which is quite arbitrary. Most of it reflects back. That's what you expect. So then I asked this question, what would happen if we fill this region with a material with permittivity near 0? Now, why we were thinking that this might actually give us some interesting solution before even we solve the problem? Because of the intuition we had in the following. If the epsilon is near 0, index is near 0. If index is near 0, the wavelength would be very long. If the wavelength would be very long, then the phase of the wave along this structure would be uniform. And if the phase is uniform, whatever phase I have over here is the same phase I have over there. So in that case, this should radiate, and by conservation of energy, we should have a very little reflection. This was one intuition. But there was another intuition was just the opposite of that. And that is, if we are inside the material and epsilon is 0, the wave impedance of the material is very high, square root of mu over epsilon. So then, in that case, we would have a huge impedance mismatch over here. So maybe everything would reflect back. Even though I have a 0 phase, but if the magnitude is 0, it's not good for me. So we decided to solve this problem to find out which one of these intuitions is true. So we got to work on this problem, and we got lucky. We got lucky because we were able to solve this problem analytically exactly. And the result is this simple formula. Very simple formula representing the reflection coefficient of this mode that's coming over here. And if I'd like this reflection coefficient to be 0, I have to make sure the numerator is 0. So let's walk over this to see under what condition this numerator would be 0. This numerator has this real part and imaginary part. Real part to be 0, which means this A1 should be equal to A2. Okay, that's fine. The two waveguides should be similar. But remember, there is no mention of the angle of this. So even it could be 180 degrees bent over here. But in order to make this thing 0, I have to make one of these three parameters 0. Okay, so what are these parameters? One is K0, which is omega over C, which means frequency 0. But that's not interesting, because frequency 0 is the DC. It means if I put a battery over here, I get the same voltage over here. Okay, so what? That's not good. Another possibility is to make mu sub r equal to 0. But this mu is the permeability of this region. Epsilon is already 0. If I make mu equal to 0, then I have impedance match. Okay, that would be a possibility. In those days, we didn't want to touch the mu. Right now, we are working on the mu equal to 0 too. But in those days, we said just stick with the epsilon. I don't want to change the mu. And the third possibility to make A sub d equal to 0. But I haven't told you what A sub d is yet. A sub d is this cross-sectional area that you see over here. In other words, if I make that cross-sectional area smaller and smaller, the wave actually tunnels through this better and better. Very counterintuitive. At first, we didn't believe that. We double-checked, triple-checked all of this, and exactly satisfying Maxwell's equation. So first, we decided to actually look at the simulation before we do experiment. Now, this is one of those cases that simulation came after the analytical result, usually. So what we did, we assumed that we have this waveguide. We put a material over here. We drew the dispersion. which has a plasma frequency omega p. And we illuminate it with this mode, and then we numerically solve this problem to look at the transmission coefficient, and transmission coefficient is this solid curve that you see over here. And you see right around the frequency close to omega p, you get a transmission near 1. And frequency omega equal to omega p means that Drude dispersion would give you epsilon 0. So it looks like it's working. And in fact, even if we add loss, still is working, but just the magnitude is coming down a little bit. In fact, 50 times loss we added, still it's working. So it's not a Fabry-Perot phenomena. It's absolutely not Fabry-Perot phenomena because you can actually change that length. And it still is working at that frequency. So just to give you a feel for it, I'm going to show you an animation over here for the simulation we have there. So imagine that we have this waveguide filled with air. And you send the wave over here. You see all of it reflects back. And this is a very narrow boundary over here. So everything inside is air. Now what I'm going to do, I'm going to put the material there. And I start bringing the epsilon down. And then repeat the simulation. So I put it 0.5. You see there's a little bit of wave start to leak out. 0.1, more is going through that. 0.001, all of it will go through that. It's quite interesting that how the wave actually tunnels through this, independent of this length. So in fact, if you look at the two extreme scenario that we have, one, no material here, everything reflects back. The other one, we put the material with epsilon near 0 over here, everything would go through this. So the three take-home message over here is this final curve that you see over here. Number one, reflection coefficient is 0. Number two, a reflection coefficient is 0 even though it's a huge geometric discontinuity. Number two, the phase inside is uniform. And that's indication of n being 0. Number three, by conservation of energy, Poynting vector here should be much larger than here. As a result, electric field is very strong. So you can actually have a field enhancement for free. And that's what we always want to have in the field of plasmonic nanophotonics, to have a very high field at a point. But now we have very high field, not only at the point, but during the entire structure with the uniform phase. That gave us a lot of ideas how to actually apply this to many different systems. So let me share with you some of the ideas here. But before, we wanted to experimentally verify that. But before I tell you how we can do experimental verification, the natural question is that, what kind of material is epsilon near 0? There are many of them. If you go to transparent conducting oxide, like indium tin oxide, this material at around 1.3 micron, the real part of epsilon is 0. If we want to go in the mid-IR, polaritonic material, polar material, like silicon carbide, at about 10.3 micron, the CO2 laser, you have a real part of epsilon near 0. Even the table salt that you have, like potassium chloride, has actually at 6 terahertz has epsilon near 0 structure. Now, my good friend Nikolai Zheludev recently actually showed that the topological insulator in the UV has near 0 properties there. But if you don't like any one of these frequency domain, you want to make the epsilon near 0 material in the frequency you like, then the concept of metamaterial will help us to put a stack of these layers together with epsilon positive, epsilon negative, to actually engineer epsilon near 0 material. And finally, those of you who are interested in microwave, there's another interesting and easy way to create imitation of epsilon near 0, and that is just pick up a parallel plate microwave waveguide, just a simple parallel plate microwave waveguide, and operate it with the TE10 mode at its cutoff frequency. You do that, you get an epsilon near 0 effective properties. Because the dispersion of a TE10 mode follows this formula, and this formula is exactly Drude model, but not with the electron density. It's a Drude model because of the height of the waveguide. So you can easily actually manipulate the effective plasma frequency of that. So we actually use this technique, and we experimentally verified that in my lab. So we created 2 microwave waveguides over here with this region, which is just air, but we operated at the cutoff frequency of that, and the result exactly followed what we were looking for. So this is a comparison of the experimental result with the theoretical result. Magnitude picked up exactly at the frequency we designed at cutoff, and the phase of the transmission coefficient crosses 0. Indication that n is equal to 0, and the wavelength inside that structure is infinitely long. And so what happens over here, by the way, again, let me emphasize something very important, that this is independent of this L. So you can actually stretch this one, happens exactly at that frequency. Better yet, you can bend it 90 degrees, you can bend it 180 degrees, works that way. We did the experiment of that. I don't want to bore you with a lot of experimental data, but we have that in the microwave. But I wanted to do it in optics. But before I show you the experiment in optics, let me show you some of these structures. So you can bend it like that, you can twist it like that. Essentially what it means, that the waveguide acts as a wire. Just like the wire that we have over here, you bend it, nothing happens to the electron flow. Now we have a scenario that you can bend it, nothing happens to the wave. Wave actually jumps over with a phase 0 across this. So one of the things came to our mind is that what would happen to actually emission of a dipole in this type of structures? Now, I showed you this picture before. Now you see if you send a wave over here, you have a very high field over here and uniform phase. So by reciprocity, if I go ahead and I put a dipole somewhere over here, anywhere over there, because the phase is uniform, I should get a good radiation out of it. Indeed, first we studied this, theoretically. So what we designed a silver structure over here with a very tiny waveguide carved into this to operate at the cutoff frequency. We put an optical emitter in our simulators over here, and indeed you see right around the cutoff of this waveguide, you have a huge emission of the dipole coming up. And it doesn't matter where you put the dipole. Anywhere you put the dipole over there is like this. Essentially what it means is you're stretching the near field of the dipole. You're stretching the near field dipole as long as you want. And that has a very interesting quantum optical implications that we are studying. So when we did this one, we were very excited, but I wanted to actually do this experimentally. But how do I put an optical emitter inside the structure that is 85 nanometer height and 100 or 200 nanometer wide, carved into a metallic silver waveguide? That was a big challenge. And I talked to some of my chemist friends to see whether they can put some quantum dots over here, but that was a challenge. Until I was presenting this in a conference, and my good friend, Albert Polman, who was the director of the Amolf Institute for Nanophotonics in Amsterdam, approached me and said, I have actually equipment in my lab that can help you to actually experimentally verify this. He told me about cathodoluminescent spectroscopy. I didn't have that equipment in my lab, but he had. So we joined forces. I went for 1 week to Amsterdam. So first of all, this is the structure of cathodoluminescent spectroscopy. Many of you are familiar with that. Electron beams is coming over here, hit your samples. Right at the location of hitting, you have a transition radiation. So you have a nanoscale dipole that you have over here and emits photon, which includes the visible domain as well. But the beauty of that is that you can determine with the accuracy of 4 nanometers where you put that dipole over there. So I went to his lab, and we put together our heads, and we designed this nanoscale waveguide. So this is the optical version of that microwave waveguide that we did in my lab. But this nanoscale waveguide was a 2 micron with a silver evaporation over here and with the silicon dioxide waveguide inside of this. We put this one in the cathodoluminescent spectroscopy. Electron beams are coming down, and we could actually scan it so that every point that electron beam hits, photons will be generated, and then this CCD camera or a spectrometer can actually collect the photons and show it as a function of wavelength, what we have. So first, let me show you what we expected to see. So this is a simulation. So what you see over here, at every point in this picture is the location of that electron beam, photons coming up, and if you look at the photon with the wavelength of 910, this would be the density of the states that we have there. Nothing peculiar over here, just like a mode of a waveguide. If in the same experiment we look at the wavelength of 624, this would be the modal structure, okay? But we're looking at the cutoff mode, not these higher order modes. These higher order modes was trivial. We were looking at the cutoff modes. Before we do that, this is the experimental results. So agreement was very encouraging for us that we have there. So then we built several different waveguides with a different width of 250 nanometer, 240 nanometer, and 180 nanometer. And then we let the electron beam go through the middle path, and for each one of these, we actually detect what would be the wavelength distribution, and this would be the plot. Location of electron beam versus the wavelength of the emitted photons, and you see this pattern. Tinier waveguide, you see this one. Tinier waveguide, you see, this is the cutoff. And now you see, in the cutoff, actually happens all independent of the location of the electron beam. This was a proof that this waveguide actually behaves as epsilon near 0 structure. Enhanced radiation we got out of that dipole. And by the way, I don't have the slide to show you over here, but we actually also measured the radiation pattern. And the radiation pattern is completely consistent with your waveguide in unison actually is radiating. In other words, the beam actually comes not at the 2 ports of the waveguide, but in the side. Becomes like an antenna array, all in phase. We have there. So then Albert and I, continued our collaboration, and we actually built that stack as well too. So this is truly a metamaterial epsilon near 0 in the visible light that we build. Now, because of this feature, we said, that's very good. If I have a very high field, I can do a lot of things over there. One thing comes to mind when you have a high field is nonlinearity. So when we were doing this, one of my good friend, Yuri Kivshar, who has done a lot of work in nonlinear metamaterial, saw our work over here. He said, by the way, why don't we join forces? I do work in nonlinear metamaterial. You do work on E and Z. Why don't we actually join forces, see what kind of nonlinear property we get over here? He sent one of his postdoc, David Paul, to my group. We already had the setup. We put actually a varactor, which is a nonlinear element in microwave right there, and we bias the varactor, and we actually do the measurement, and you see actually the system would self-tune itself. As you change the microwave power, actually that varactor changes its epsilon, and the system actually works in a very nonlinear, very nice way there. That was in the microwave domain. But recently, by the way, in collaboration with my good friend Luca Dal Negro in Boston University, we decided to actually do this in the near IR. And Luca can actually make ITO, indium tinoxide, which is actually very good E and Z material, as around 1.3 micron. And indeed, we showed that inside you can have a very high field, and you can have actually third harmonic generation enhancement due to the fact that you can actually enhance the field inside the structure. And I know my good friend Professor Boyd has a lot of interest in nonlinearity in E and Z, and I very much look forward to talking to you, Bob, today and tomorrow with your students in this regard. Another thing to do is that whenever you have high field and uniform phase, another application comes to mind. How about if we use it as a sensor? If you have high field, you can actually bring the height very, very small, so you can actually have a high field almost for free. For free, meaning that you don't need to have a very high energy over here. You can make a high field by actually bringing the height down. So actually, it's a very simple formula. Ratio of this height over this height would give you the field enhancement. Very simple. So what we decide to do is to actually have something which we call it E and Z transistor over here. So what you can do, you can actually change the epsilon over here, and that hugely is going to change the output. It's kind of like a gate and source and drain. So one of the things we are studying right now is to look at the possibility of using this in microfluidics. If I can send the fluid through here, as the fluid goes through here, actually I can see the variation of that at the output. And these are some of the result that this is our result of our analytical study that shows that indeed this will work. Now, one of the things that caught my attention as we were working with this E and Z structure is that there's another similar, not similar, but analogous effect, by the way, in superconductivity. Now, in superconductivity, effectively mu is equal to 0, effectively. But that's actually better yet to be called extreme diamagnetism that we have there. Now, because of that, the magnetic field B cannot enter into the structure. That's one of the reasons that the magnet can actually levitate there. So we said, wait a second, actually epsilon near 0, vector D in Maxwell's equation cannot enter. So is there an interesting analogy? Can I have an equivalent of electric field levitation rather than magnetic field levitation? So we decided to study this. And actually, if you compare, what happens to the magnet over a superconductor is a complete analogy to if you have an electric dipole over the region with epsilon near 0 structure, with a big difference, that this can never be in the DC signal. You cannot have epsilon near 0 in the DC. It has to be dynamic. So as a result, this dipole has to be a dynamic dipole. It could be an optical dipole that you excited with a laser. It could be a microwave dipole that you excited with as an antenna on top of a structure that would behave as epsilon near 0. Now, we studied this, and we got actually surprising result. In fact, if you take a look at this, you see this is the height of the dipole, the structure, versus the value of the epsilon of the substrate. And you see there are two different colors over here. The red one means repulsion, levitation. The blue one means attraction. So if the epsilon of the holes is between -1 and +1, you actually get levitation. You don't need to have epsilon equal to 0. Any range between -1 and +1 would do. Now, at first when we studied this, we said, okay, well, maybe the loss is going to kill that. But actually, this is one of the phenomena that it's very robust to the loss. In fact, in this case, the imaginary part of permittivity is 0. In this case, we put 0.8, very, very lossy structure, and still the system works. So one of the things we are planning to do is to actually show this first in the microwave, then we're going to go into optics to see whether we can levitate nanoparticles. And if we can do that, that could be quite interesting from the removing of the friction. So if I illuminate it with a laser and the levitate particle, then the fluidic can actually move it without having, kind of like a magnetic levitation for the train, but that would be for the nanoparticle, but for the dynamic scenario. And you will hear from my good friend Modi Segev in his talk. He's one of the pioneers of photonic topological insulator. It turns out that the ENZ can have somewhat similar property if you magnetically bias it. If you magnetically bias it, you can have a scenario that the optical signal actually only have a surface state, but not the bulk state. So you can actually go around this, and then you can actually have a cavity that the light gets in, and the only way to get out is through another part. It's immune to defects, and it's really protected, topologically. Now, so this was what I take you back and how we introduced ENZ and brought you back to right now as some of the effect over here. But in recent years, particularly in past year and a half, we got very interested, and for the reason that you're going to see, is to explore the following. What would happen if both epsilon and mu near 0? Now, why? Why not just stick with epsilon 0? We already have it. Because in the case of epsilon 0, one limitation was the height. I had to make the height small in order to have a wave go through. If I make a height large, we have a lot of reflection. So I wanted to have that restriction removed. And I went back to the formula we have in our PRL paper in 2006. You notice that there was another one, mu r. So I said, what would happen if we make mu r also equal to 0? So we decided to look at this, particularly with this concept that could we actually macroscopically decouple electricity and magnetism? And what would happen to the quantum optics of that? What would happen to the device aspects of that? So let me tell you, by the way, first, the thought process that we have. Imagine that you have regular waveguide again, with a PEC wall filled with air. And imagine you have a simple mode that's going through this. Very, very simple. No reflection, transmission is 1. Now what I'm going to do, I'm going to come over here, cut this waveguide in half, put 1/2 over here, 1/2 over there, and I'm going to ask this question. What if I want to fill the region between these two waveguides such that the observer at the input and the observer at the output would not know that this waveguide has been cut? In other words, what should be the material inside this structure with the arbitrary shape, this is not a fabric Peru, with the arbitrary shape such that the transmission coefficient would be exactly like what you have over here. In other words, I want this entire region to behave as one point electromagnetically, even though you can have any size we want. And the answer to that is you have to have a structure that epsilon and mu both will be near 0. Now, so let me show you first an interesting simulation that motivated us. So imagine that we go over here and hypothetically we put epsilon and mu equal to 0, solve Maxwell's equations. You get this. This is a magnetic field distribution of the mode that you see over here. You see very nice propagation. This is just a regular wavelength over here. Inside, wavelength becomes infinite. As a result, everything is moving with unison. That's for the magnetic field. But for the electric field, it becomes like this. For the electric field, it becomes like this. And in fact, it's very interesting because in this structure, curl of E is equal to 0, which means the line integral from here to here would stay the same. That reminds us of Kirchhoff voltage law in circuits, but now you can do it in optics. So you can actually completely bring the Kirchhoff voltage law in optics, make the curl of E is equal to 0, make the Faraday's law to be 0 on the other side from macroscopic point of view. Now, this encouraged us to see what would happen if we have such a structure. And you notice over here, it doesn't matter where you put the ports. You can put the port anywhere you want. Reflection is 0, transmission would be 1. Doesn't matter it goes like this, or it goes like this, or it goes like this, it goes like that. That entire region becomes one point electromagnetically. But, of course, the natural question is that what kind of interesting effect it has in quantum electrodynamics. That's one of the things we are studying right now. And if time permits, I'm going to show you ongoing results that we have right now. We want to study superradiance of this to see what kind of superradiance we have in such a structure, because wavelength essentially is infinite. Near field is stretched. So the two emitters over here, in some sense, feel that they're in the near field of each other. How about subradiance? How about long-range collective states of multi-emitters? How about long-range entanglement? Can I entangle two states, even though they're far away, but by having this structure in between, because effectively should work as one point? How about cavity quantum electrodynamics of this? But before we get to all of this, and this is an ongoing work, the question is, how do we make such a structure? I already showed you how we make E and Z. But how do we make such a structure in which both epsilon and mu will be near zero? Mu usually is much tougher to deal with. Particularly, you don't want to use magnetic material, because magnetic material has a lot of loss, a lot of headaches. The question is, could we actually do this without using magnetic materials? Just by using structures, just by using proper design, by using dielectric. Okay, let's see what we can do. I already showed you this slide, how you can have epsilon near zero. That, we have several examples. You can use actual materials if you like to. You can use engineered material if you like to. So do the following. Let's take any one of these examples as our E and Z host. And now let's do the interesting things. Let's assume I get, this is for a moment the two-dimensional scenario. Let me assume I get the structure that the host is epsilon near zero. So one of those examples I showed in the previous. Now what I would like to do, I would like to make this structure look like not only its effective epsilon is near zero, but its effective mu is zero from an outside world, because I want to look at it macroscopically. I'm not interested in the local effect, but I'm interested in the global effect. So here is one way. You can actually come over here and put a dielectric rod inside this structure. This dielectric is simple dielectric. You can use silicon, you can use anything you want, you put it there. Then, by choosing the size of this, and given the epsilon I, which is the regular dielectric over here, then it is possible to actually design this such that the effective permeability also will be equal to zero. Now, just to give you an intuitive feeling how you can do it, let's do the following. Let's assume that this dielectric rod has a circular cross-section. If it has circular cross-section, the formula becomes very, very simple. In fact, this formula is actually our prescription. That if you look at this formula, you notice that you can design the radius of this dielectric rod, the epsilon of this dielectric rod, and the area of this cell such that this effective mu becomes zero. Very simple recipe. I'm going to show you that actually how we have done this. But before I show you, there is another way you can actually make the effective permittivity and effective permittivity zero. And that's by using photonic bandgap structures. Professor C.T. Chen from Hong Kong University of Science and Technology showed that if you design the structure with the photonic bandgap structure such that you actually operate at the Dirac dispersion with the accidental degeneracy, you can have an effective index near zero. So that's another way of doing that. So let's go to this structure that I showed you over here, and imagine I want to use it as a cavity. So what I'm going to do, I'm going to have a closed cavity over here. The background is epsilon near zero. I put a dielectric over here with the epsilon, normal epsilon, like 9, and so on. And with the diameter about, lambda over 4 is a reasonable structure. And this is the field distribution of a resonant mode over here. But this cavity is a very strange cavity. Because whenever we have a cavity that has certain high Q, if you change the boundary of the cavity, the resonant frequency will shift. If you change anything in the cavity, resonant frequency would shift. But not this one. This cavity is actually immune to the change in its shape. So you can actually move this dielectric rod here, resonant frequency does not change. Field distribution changes, but resonant frequency does not change. You can even keep the area and just change the shape in any arbitrary way you want. This one, this one, this one, this one, this one, this one. All of these cavities have the same resonant frequency, but very different field distribution, as a result, different Q. So you can actually have a very interesting scenario that you can decouple your design of your resonant frequency away from the design of your line width. So you can have a different line width without actually moving the things there. So we actually look at the 3D scenario of this. I don't have time to go through the detail of that, but 3D scenario is even more interesting because the volume doesn't have to stay the same. You can even change that. So here you can have a structure with this topology. You can have structure with the foreign objects added to it. You can have a structure like this, and all of these have the same resonant frequency. And you can actually put some dent into this cavity, change this dent. You can change the Q, but not its resonant frequency. This is resonant frequency is the same, but the Q can change. So we decided to actually experimentally test this in microwave. And so this is the setup that we designed. 3 different cavities, intentionally 3 different shapes, with a dielectric rod in between that we can put in 3 different locations. So we have 9 different cavities, if you will. Actually, we have 3, but we just moved the rod 3 different ways. And before we did the experiment, we look at the simulation of that, and simulation was encouraging according to our theory. This means the resonant frequencies stay over here, doesn't matter what shape this cavity has. So we build the cavity in the microwave. These are the structure that we build over here. And just 2 weeks ago, we finished the experiment. And right now, we are actually going over the data, and data actually supports that. Now, we still need to do more work in order to make sure that everything in the experiment is completely 100% double check. But right now, the preliminary result that we are getting after the post-processing of experimental results are very encouraging. Hopefully, in a month or 2, we're going to submit the manuscript. So finally, what kind of interesting interaction of dipole-dipole in quantum emitters this will have? I mean, we are looking at some of these as ongoing ones. So let me just show you some preliminary results of this. So imagine I have 2 quantum emitters I put next to each other in a regular waveguide. And when we do that, of course, we know that the decay rate and the resonant shift of the atomic transition, of course, would change because of the effect of the other dipole, like a Dicke state and so on we have here. Obviously, that depends on the separation of this, and we all know that's a very standard problem. But what I want to do, I want to do this. I want to cut this waveguide again, as I mentioned before. I want to put this cavity between this, and I want to bring these 2 dipoles back over here and study, again, the collective interaction depending on the coupling coefficients that determine the decay rate, spontaneous decay rate, and also the frequency resonant shift of this transition. So if you follow this standard formula and we apply it to this case, let me assume, for example, in this case, we choose one of those cavities that I showed you over here with the dielectric rod over here, background E and Z. We put the 2 dipole in our study. This is the theoretical study we have. So what we're going to do, we're going to move this dielectric rod around. And as we move, we're going to calculate this collective interaction and compare it with the collective interaction before we put the cavity and find the difference and find the normalized difference, this expression. And when you do that, you see, as a function of changing this location, the difference is extremely small. In other words, these 2 dipoles, these 2 quantum emitters, they feel as though they're in the near field of each other. No matter what you do with the dielectric rod there, no matter what you do with the shape of that cavity behaves as 1 point. And so far, also from quantum optical point of view, it looks like 1 point. Now, that remains to be seen. There's a lot of things we still don't know. We are trying to study some of the cavity quantum electrodynamics of that. So people would say, okay, if you do this, how are you going to do that in microwave? I want to do that actually in optics. But in order to do in optics, I cannot use regular metal because the metal would be lossy. So we decided to design a photonic bandgap structures with the intention that in the future, hopefully in the near future, we would like to do experiment. So what we did, we designed this structure, just made of silicon, just simple silicon, except this region is designed to have effective index near 0. This region is designed to actually have a bandgap, so nothing will go. So we have 2 waveguides coming like this. So if we look at the 2 dipoles over here and look at the field distribution, this would be the magnitude and phase field distribution you get over here, independent of where you put the waveguide. Here is one case, here is another case, here is another case. The 2 dipoles should feel the same way to do that. Of course, this is just a theory so far. We would love to do this experiment. That remains to be seen. So work in progress. What I'd like to do is to combine this type of crazy cavities with break-of time reversal symmetry. In other words, what kind of entanglement I have if I bring non-reciprocity over here. And that's some of the things that we are working on that right now. Could we actually break the entanglement in an opposite way? This can entangle with that one, but that one cannot entangle with this one. We'll see. So let me stop over here, the summary of the work that we do, that indeed, as Professor Harosh mentioned, we are in the area that, with the proper design, you can have a very unusual light-matter interaction. In this particular case, we are looking at the platform, an extreme platform of light-matter interaction, such that you can have scenarios that will give you extreme parameters like extreme dimensionality, extreme information processing at the nanoscale, and this topic that I talk about, extreme parameters, whether epsilon 0, mu 0, index near 0, and all light-matter interaction. With that, I thank you very much for your attention. Thank you.
So, Nader, thank you very much. Fantastic talk.
Thank you.
You had me you had us on the edge of our seats.
Thank you.
We are running short, but there is time for some questions. Oh, but lots of questions. Many Iranian questions, as it turns out. Ebri, maybe you first.
Yeah. So fantastic stuff, fantastic talk. So, would you please comment on the exchange of momentum with a near zero index?
Mm-hmm.
So because I see a discontinuity, huge discontinuity there, and huge force. If I'm
yes. I mean, the momentum is there, but the momentum is fine. In other words, what happens is the following: that if you look at the, energy momentum diagram of this type of structures, if you have an unbounded epsilon and mu near 0, then the group velocity would be 0. But the question is, you never have unbounded system. In all these cases that I showed over here, the system is always bound, which means there's an input and there's an output. So the structural dispersion comes into play, and that actually is the reason that the energy actually goes through this. That's one reason. Another reason is this is one of those cases that actually loss is good for us. Because if you look at the energy momentum diagram, just a simple parallel plate waveguide or simple Drude model without a loss, if you bring it to omega p, obviously your epsilon is 0, but then your phase velocity becomes infinite, your group velocity becomes 0. However, if you introduce loss, which any natural structure has loss, then the energy momentum diagram, by the time it gets close to that, actually is a band bending. And that band bending would give the slope, which is not 0. And that's how you have group velocity that can go through.
And Hani was next.
So if I understood you correctly, you said for this waveguide and the bridge, if you change the height, the enhancement, that the free enhancement that you get for this field is the ratio between the height of the waveguide. Okay, there is a limit, yes? And how much you can enhance?
Oh, well, conceptual, in principle, you can enhance it as much as you can bring this height closer and closer. Now, you don't want to have a short circuit, because if you have a short circuit, all the wave would come back. So you should not have any current tunneling from the top to the bottom. So you can bring it close enough that the electron would not tunnel. If the electron would tunnel, then you get a reflection. So, but that means that you can have actually good amounts. For example, in the optical experiment we did, the height was 85 nanometers. We got a very good enhancement there.
What was the enhancement?
I don't remember it right now over here. I can show you, by the way. We have the result. I think it was about maybe 10, 15 of that, because that was slightly different because we had the electron beam coming like this, rather than the energy coming from the outside waveguide. So the enhancement was different enhancement than what we want. In the case of microwave enhancement, the enhancement was something like 100 times. But in the microwave enhancement, that's not surprising, because you can have a coaxial cable that the electric field inside of that is very high. But the interesting point about this is that this system actually doesn't have an inner conductor. In other words, you can actually play around with the dispersion of the structure to the advantage of the system you'd like to design. And I'd be happy to talk to you in the detail of that.
There's one more question in the back. That was the third hand that went up.
you briefly touched on this, especially our answer, but how one in ideal is 1-to-1 very high field enhancement, but also we want to have low group velocity.
Yes.
To do something. So how do you manage the group velocity?
Excellent point. Actually, that goes hand in hand. Because as you bring the height of that waveguide closer and closer, field will be enhanced, but the bandwidth becomes narrow. And when the bandwidth becomes narrow, your group velocity go down. So that's exactly what you want if you are after the slow light. structure. That would help you with the additional advantage that the structure doesn't have to be straight. You can bend it, you can squeeze it any way you want.